a philosopher has a gun to my head and is asking me, what do you think? Then I would have to say I don't know.
Hello and welcome to Physics Chat Season 4, the show where we talk to physicists about their life and research. As you can see, I'm new here, so let me introduce myself. My name is Tian, and I'm a second-year PhD student at the University of Portsmouth. I'm studying cosmology and gravitational lensing. And I do astrophotography for fun, so I enjoy looking at the night sky. Today, I'm joined by my co-host Susanna and Sergi. And how are you both and what you're most looking forward to in the Season 4?
Hello, everyone. I'm looking forward to meeting our guests and hearing about what they get up to. What about you, Susanna?
Hello, I am most looking forward to the random question, obviously my favourite part of the show. What about you, Tian?
Well, I am looking forward to being on the show and asking the guest about other questions. So, let's introduce our first guest, Ashim. How are you, Ashim?
I'm great, thanks.
Right, so can you describe your research for us?
In short, I work on tests of gravity. So I work with Tessa Baker, who's also at Portsmouth at the moment. But what that means in practice is that I make predictions for various theories that you can compare with experiments. So that can take some theory work, and in my case, also some simulation work that you can compare with some data from telescopes, for instance.
Okay, we already got loads of keywords here. Can you first tell me what is modified gravity?
So modified gravity is, if you have a baseline theory like general relativity, then any modification to that would be considered modified gravity. Now, what I mean by baseline is that it is the current theory that is accepted by the community, and that's because it explains data fairly well. But there are a few places where you might want to do things better, and that might be, for instance, to explain why the universe is expanding at an accelerated rate. The answers within general relativity, or GR, can be a little unsatisfying to some people. So if you modify gravity and come up with a new explanation, that's modified gravity.
Okay, could you expand more on why are we so keen to replace it when it actually seems to work so well in some places?
There are a few ways to think about that. There are some theoretical reasons, for instance. So I gave one when it comes to the accelerated expansion, so I can be a bit more specific about that. So basically, to explain the expansion, what you have to do to the equations is add a constant. Then what you do is you use data to tell you what the value of the constant is to match what we are actually observing. At the same time, you can also try and get a theoretical prediction from your theory, so on pen and paper or on the computer, to try and understand what you would predict just from following our various principles. So if you've heard of quantum field theory, in that theory, you have a concept called the vacuum energy, the energy of the vacuum of empty space. And you would traditionally associate that with the cosmological constant, because the constant also is something that would exist in the vacuum with no matter present. But there's a hilarious mismatch between the value you get in QFT, quantum field theory, and what you get in GR. And that mismatch is a problem for some people, and they think it's a theoretical problem, meaning that, for instance, GR could be the reason why it's not working. And so you may come up with a new theory in order to actually make the two results match better and therefore have a more consistent explanation. That's one way you could do it. I'll just briefly say that there is another reason for wanting to test GR, and that's just because there's no reason to just accept what you have. So we may go into this later in this, of course, but if you're a fan of Karl Popper, your knowledge is as good as how well you can falsify things.
Right. So actually, I know Sergi is also studying modified gravity, but what I see all day, he's dealing with lots of long equations in the office.
Yeah. So I also do modified gravity, and in particular, I think we're looking at the same kind of modifications to gravity, Ashim and me, but I think we do it in a very different way. So I use gravitational waves to do these tests, but Ashim, you said you use some kind of simulations. Can you expand on that?
Sure. So yes, we do look at modified gravity in slightly different ways. I look at what's called large-scale structure. So that's just looking at how matter clumps together as it experiences the forces of gravity. In particular, it's when matter clumps to form what would eventually be the hotbed of galaxies or clusters of galaxies. So you may find the word halo, for instance, thrown around. It is thought that in these dense or overdense regions of space, galaxies tend to form. So that's what halos are. By simulations, I mean that I consider n-body simulations. So I take various particles of matter, I let them experience the forces of gravity, and I numerically solve for their motion. And over time, they will start to cluster and then give you the kind of clustering behavior of the theory. The reason why it has to be done through simulation and not, for instance, it's not something I can predict on pen and paper very easily, is because I'm specifically interested in the so-called nonlinear scales. It just means that I'm looking at scales of the universe where the distances between objects are not tremendous in a cosmological sense. So obviously all the distances I'm talking about are far removed from everyday experience. But if we just consider for a moment that I think about galactic distances being small, then in that context, I am looking at small distances, and that can't be modeled very well using theory, because a very typical way to model in theory is to take a known solution and then perturb it. You look around known solutions, and that doesn't work very well if you go far away from the known solution, which is precisely what happens on these scales. And that's why I need to use the computer that does a kind of brute force calculation, if you like.
Right. So there is a keyword that I think relates to what you're explaining here, and it would be great if you could explain that for us. And it's the power spectrum. And also, how does it characterize these modifications to gravity?
Right. So the power spectrum is what's called a summary statistic. It's a good quantitative measure. It's a good number that tells you how clustered your matter is. It's not the only way you can tell how clustered matter is, but it's one of the first statistics you can use. So the way it works is that you take 2 points in space and you ask yourself, what is the probability above random that you'll encounter 2 overdensities? So this is matter that is more dense than usual at the 2 points where my hands are. And you do this for every single point in space. So you keep asking yourself for all kinds of separations across all over space. You keep asking yourself, is it over random or not? Is a good way to start asking yourself, how clustered is your matter? That's why I use it.
Right. And then, so I imagine there is something we expect. So like a prediction of GR or something, that an answer that we can expect. And then if we find alterations to that, that can be a source of modified gravity. Is that the idea?
That's right. Of course, one of the problems is that many sources can give you deviations from the expectation. And that is a challenge, of course. That's something that one has to be worried about. The point is that one has to be a bit careful about attributing the difference you see. For instance, if you measure data to some effect. So I may be looking for modified gravity, but there could be other reasons for why. But yes, you're absolutely right. You would take the prediction, say, from GR. You'd ask yourself, does that match the data? And if it doesn't, well, there you go. Now you need to find another explanation. And therefore, you may then give a modified gravity theory instead that does things better.
Well, that's a lot of information. Thank you, Ashim and Sergi. We definitely have lots of things to digest. Oh, speaking of digest, it's time for the random question. What is the weirdest food combination you enjoy?
Weirdest food combination? There have been several combinations I've done that are questionable to my friends and my former flatmates who had the misfortune, I guess, of seeing what I would do. I think, like many people, if there are things left in the fridge, there is pressure to finish them. I don't shy away from combinations that involve, for instance, a block of cheese that may go bad soon, rice and some sausages, for instance. It does work. It's not traditional or conventional, and you may get weird looks for it. But if it tastes good, then what can I say?
That sounds an amazing combination.
Do you have one, Susanna?
There is a very interesting combination. I lived with some Chinese flatmates, and they cooked amazing food. And they would also feed me because I have a face that looks like feed me, which I do appreciate. And they fed me hot pot, and I got to try so many cool things, such as duck tongue, I think was my favorite.
Yeah, let's get back to research, Ashim. You mentioned that the GR, or general relativity, is the best theory of gravity. If we have a bad theory that describes almost everything, should we study the alternative theory of that one? And why should we do that?
The thing that people may pick up on is the way in which you phrase the question, right? If you have a theory that describes almost, you did write almost, just to give a qualifier, almost everything, then should we keep going to try and find other theories? In one sense, if you have an almost, then yes, because there are some people who want to describe actually everything. And that's where people get the theory of everything type ideas. There is another sense in which people may address this question. That might be, even if you had said, if we have a theory of everything, should we keep going? The point here is that, what does it mean to have a theory of everything? How do you know you have a theory of everything? And what this is related to is how you think about science and how you uncover the truth, if it exists, and things like that. And this is one topic that I've been interested in for a while. There's this impression that I feel, especially when I was a kid, that when you study science or you're a scientist, what you do is the truth. You uncover the truth. Everything else is maybe play acting or fanciful and sweet and cute, but it's the scientists that are really doing the real stuff, and you can see it works, because if I pick up a phone, you'll be, well, this is a product of science. If I point at a TV, it's a product of science, and we are talking because of science over the internet and blah, blah, blah. But I think there are a few things that aren't talked about very commonly. Of course, there are many people who are interested in the philosophy of science. One thing we have to remember is what we assume when we do science. I think actually these things are not talked about enough. So how does this relate to Popper? Popper was one of the thinkers that brought in the idea of falsification quite strongly into science, because before Popper, there was this inductive view on science, which is basically scientists observe the world and they sort of infer a natural law. They imagine that these observations are happening because of a law, but you have no way of proving that. It's a bit like you've conjured a story, but there's no reason nature actually follows the story at all. It might match your story up to a certain point, but then it can diverge later. And so that's the whole thing that Popper's talking about. You don't prove things, but what you can do in science, when you do experiments and you match them, is you can show when something is wrong. And actually, that's really important. It's really important to have a theory that is capable of being wrong in the first place. And GR is capable of being wrong, which is nice. So you can disprove it. And I would expect that any theory in the future would be like this. So even if we had a theory of everything, it should be falsifiable. So it should be possible to show it's wrong. And that always gives you an opportunity to come up with something else.
So on this topic of philosophy, I have a tough question for you and also our audience. So please let us know in the comments section what you think about this question. If a tree falls in the forest and there's no one around to hear it, does it make a sound?
Right. So I'm one of the one worldview that I found quite attractive to think about is that our sensory perceptions make up reality. While it is convenient to assume there's an objective natural world that exists outside of what you perceive, it doesn't necessarily exist. There's nothing about that world that you can prove. You assume it, but you can't prove that. So if we take the tree, for example, if I did not see the tree, I did not hear the tree, there's nothing about my perceptions that indicates that I ever knew about this tree and that it fell or anything like that, then I cannot say with any confidence that it did fall, that it made a sound or anything of that sort. And I would not necessarily conclude it's real at all. I would concede that it is convenient. Let's say if I had seen the tree a day before it fell, and then the day after it fell, I saw it had fallen, then it is convenient to think about there being a world that exists independently of what I perceive, where the tree did do its own thing. It fell, and maybe I could connect it to other trees I've seen falling in real time, that it makes a sound while I'm doing that, while it does that. But that's a convenience, I think. It's not necessarily something you actually know or can directly say that I've perceived. So that's why I would say it depends, which is obviously a very convenient, possibly boring, or possibly interesting response, because obviously it means you can talk about what do you mean by it depends. But I am the kind of person who thinks that ultimately, when it comes to personal confidence, it's about what you've actually seen. So if I didn't see it, then maybe I'm going to be the type of person who annoyingly questions someone and says, really? Did you see it? And, for instance, and go on in that way.
Yeah, that's an interesting question and answer. I think when people usually try to answer it, they do it in terms of our definition of sound. And so you can define sound as the vibrations of the air. That would be the physical phenomena of sound. And you can also define it as our response to those vibrations. So if it's the latter, if it's our response, then there needs to be an ear there or a hearing device or something that can respond to those vibrations. So in that case, yeah, I would say it doesn't make a sound if there is no one there, because there is no one to respond to it. Or if you define sound as just the vibrations, then you can say, yes, it makes a sound because vibrations are there, even though there's no one to hear it.
So even if we went with physical sound being vibrations of air, I would still need to hear it to acknowledge it, in the sense that the vibrations of the air would be like the inductive step we talked about, but this inductive step does not matter if I wasn't there to actually record this observation, or if I didn't have a chain of events that I had trust in. So for instance, let's say if one of you heard it, and then you told me that you heard the tree, then I could accept your view and say that, yes, I accept that you observed it, and therefore I will accept it as having happened, even though I have absolutely no direct knowledge and I have no reason to really believe that that actually happened. An event is accepted or acceptable when there's a responder. Yeah. As in when there is someone to hear it, someone to respond to it, then it is a lot easier to say something happened than when not.
That sounds like quantum mechanics.
It does sound a bit like how quantum mechanics places great importance on the actual observation. So just by observing, you do something.
So let's try to understand your viewpoint a bit better. I guess the question is, what do you consider reality to be? So in the case of the tree, for example, no one is there to see it. And physically, as we said, we describe sound as the vibrations of air, but there is no one there to see it. Would you be ready to accept that there are vibrations in the air there when this happens, or that the tree exists when no one is looking at it? Or is reality just the collection of your own mind states and responses to something that you don't actually know what it is?
If I had to give the most serious answer, the one where a philosopher has a gun to my head and is asking me, what do you think? Then I would have to say I don't know. To be absolutely honest, I don't know. But what I would, because you did ask in the sense, would you accept or would you believe? I would actually. So I would believe that if a tree fell, that it did make a sound. And I would believe that if I could do a repetition of the event and put an observer there or put myself there, I would hear a sound. But that's a belief. The point that I'm making here is that for me to say this, it's a belief. I have no real conclusive reason to prove that. I can only believe it.
Okay, and so if you were there next to the tree and it fell and you heard it, would that be a belief or would it be full knowledge?
That's a very interesting question. It would be tempting to say it's knowledge. You've observed it now directly, right? You are not relying on anything else, just your own perception. But there's a lot of work, I think, from observing the tree falling to then coming up with a statement like, yes, I believe a sound happened. Yes, I believe it was the tree. And I believe it was the air vibrating and things like that. But I think there's a lot you can do. And I guess this is why people also find philosophy frustrating, right? Because it takes so much time just to talk about a tree, when intuitively, for instance, someone might say, of course it was a tree. What else is it going to be?
Yeah, thank you very much for your answer. Just to finish on that. Yeah, so looking at the tree and hearing it and seeing it fall and hearing the sound, that would count as justified belief. And let's imagine as well that it was true for some reason, right? So it was a justified and true belief. But your argument for why this can sometimes not constitute knowledge is actually the same argument that was made by one of the most influential papers in epistemology. And the whole thing is known as the get-here problems. And yeah, it's the proof that justified true belief is not always knowledge. So yeah, thank you very much for that. We'll put a link in the description for the paper if anyone wants to read it.
Thank you very much for being on Physics Chat, Ashim. We have lots of conversation on the philosophy. So let us know in the comment section if there's a tree falls in the forest and there's no one around to hear it, does it make a sound? We would love to hear from you, but from everyone at Field of View, we hope you have a great day and goodbye.
Bye.
Thank you. Bye-bye. It's really important to have a theory that is capable of being wrong in the first place.